Here we will develop a model of ferromagnetism. The model that we will derive is that of the Ising model. The Ising model is a very ubiquitous model that describes a lot of processes from ferromagnetism to protein folding or movement of molecular motors in our body. First, let's recap what we know about magnetic fields. The magnetic field that a magnet or an electric coil generate in vacuum is characterized by the magnetic field strength H, which has a unit of amps per meter. Inside a material, the magnetic field is characterized by the B field, the magnetic field induction measured in Tesla. The magnetic field inside of a material is given by the sum of the magnetic field from the outside, H, plus the internal magnetization given by the polarization of magnetic moments inside of the substance. Now, the polarization of these magnetic moments are influenced by the product of the external magnetic field H times prefactor 1 plus chi, where chi is the magnetic susceptibility of the substance. The magnetic susceptibility is the partial derivative of the internal magnetization with respect to H. We distinguish three types of magnets. There's paramagnetism, there's ferromagnetism, and there's diamagnetism. The paramagnet we already described when discussing the canonical ensemble. Paramagnetism is characterized by magnetic moments in a material that can be polarized in an external magnetic field. Typical substances are tungsten, cesium, aluminum, lithium, or sodium. Paramagnetic materials are attracted towards the external field. Diamagnetic materials, in contrast, are expelled from the magnetic field. Typical materials are gold, water, or superconducting materials. In the image, you see a frog that is levitated in a high magnetic field in the high magnetic field lab in Nijmegen, an image that earned André Geim the IG Nobel Prize in 2000. Paramagnetism we discussed in one of the earlier tutorials. What we found there is that we could explain the magnetic saturation behavior of the substance simply given by the limited number of magnetic moments in a substance that saturate at a given field, and we could explain the typical temperature dependence of the magnetization that drops like 1 divided by T given by the Weiss law. Today we will look into ferromagnet. A typical ferromagnet is iron. If you place an iron rod into a magnetic field and increase the magnetic field strength, what you will find is that the magnetization of the iron will increase. Yet if you now reduce the external magnetic field, you will find, in comparison to the paramagnet, for which the magnetization would drop to zero again, that even at zero external magnetic field, there is a residual magnetization in your probe. And you would have to inverse the external magnetic field to obtain zero magnetization back again. Hence, ferromagnets display a hysteresis. Although there is no external magnetic field, there is magnetization. This is what we would like to explain. And there are further observations that we would like to include in our explanation. There is a particular reduction of the residual magnetization as a function of temperature. There is a critical temperature Tc for which the zero magnetization disappears. For iron, this is 1043 kelvins. The model to describe those observations is that the magnetic moments in ferromagnetic materials interact with each other such that if you switch off the external magnetic field, the orientation of the magnetic moment stays. Let's make up such a model. The model we make up is the so-called 3D lattice Ising model. We assume that our material is a crystal where on each lattice side there's one magnetic moment. On one hand, this magnetic moment will interact with the external magnetic field H, yielding a side energy of minus H times the magnetic moment, and there is an interaction between two magnetic moments characterized by an interaction energy minus J sigma I sigma J. Further, we assume that these magnetic moments are spins, the quantum unit of a magnetic moment in which the value of the sigma i's can be either plus or minus 1, corresponding to either parallel or anti-parallel to the external magnetic field. In order to roll out the statistical physics description of such a system, we first have to derive the Hamiltonian. The Hamiltonian is characterized by the site energies epsilon I equal to minus g mu naught mu Bohr h sigma I, where g is the gyromagnetic ratio for an electron, this is 2, mu 0 the vacuum permeability, and mu b Bohr magneton, the magnetic moment of an individual spin. And the interaction energy minus j half sum on all j not equal to I sigma j. In our discussion, we will abbreviate all the prefactors in front of the magnetic field strength H and gather it together into one H, where H is the external magnetic field. Further, we do now a few assumptions. The first is that all spins are located in a d-dimensional square lattice. And we allow only for nearest neighbor interactions. We know from electromagnetism that typical interactions between two dipoles scales with the distance to the power 3. Hence, interactions will die off very rapidly, and it's conceivable that we just consider the nearest neighbor interactions. Now, both of those assumptions lead to the total number of neighbors that each spin has is equal to capital C, which is equal to 2 times the dimension of the system. Each spin has 2 neighbors in each direction. As the interaction potential depends on more than one spin, we cannot apply the tricks that we used for the ideal gas. And we have to come up with a different solution, and the solution that we will look into today is the mean field approximation. In the mean field approximation, we assume there is a mean mechanization, sigma bar, such that I can express the mechanization of a single spin, sigma I, is equal to sigma bar plus delta I, where delta is a small value. Now let's have a look into the sum on the interaction. The sum on all I not equal to j, where we assume only nearest neighbors, sigma I times sigma j, and use our definition of the mean mechanization. This is equal to the sum on all j, sigma bar plus delta I times sigma bar plus delta j. In calculating the product, we obtain 3 terms. The first is sum on all j, sigma bar squared. The second term is equal to sigma bar times sum on all j, delta I plus delta j. And the last part, where we have the sum on all delta I times delta j. Now, in the mean field approximation, we assume that this last term is equal to 0. What we actually do is that we neglect correlations in the spin values. Doing this approximation and filling in again the definition of the delta i's, we obtain the final expression that the sum on all j, sigma I, sigma j is equal to minus c times sigma bar squared plus sigma bar sum on j, sigma j plus c times sigma bar, sigma I. With this, we now calculate the total Hamiltonian. The total Hamiltonian is given by E is equal to the sum on all I epsilon I, which is the sum on all I of the above expression plus the initial term h sigma I. Considering also the sum on all I, we see there is a symmetry in the last 2 terms of the above equation, namely that sigma bar times sum on all j, sigma j, and sigma bar times sigma I, sum on all I, is equivalent. Hence we can rewrite these terms to 2 times c times sigma bar times sigma I, and only sum on I, finally leading to the expression that the total Hamiltonian is given by sum on all I, c half j sigma bar squared minus h plus cj sigma bar times sigma I. We achieved what we wanted. The total Hamiltonian is now just the sum on all site energies epsilon I. and independent on the spin values of any other site, meaning our system is explained in terms of the ideal gas. Let's assume the canonical ensemble. The n-particle partition function z of n and beta is then given by the single particle partition function z1 of beta to the power n, which is given by the sum on the two values of sigma plus and minus 1 e to the power minus beta epsilon I, leading to the final result of z of n and beta is equal to e to the power minus cn half j beta sigma bar squared times 2 to the power n times cosine hyperbolic to the power n of beta h prime, in which we use the definition of the hyperbolic cosine being e to the power x plus e to the power minus x. Now, from the partition function, we also can derive the value of the mean mechanization. Sigma bar is equal to the mean mechanization divided by the number of particles, given by 1 divided by n times 1 divided by beta del log z by del h. Now, doing this derivative, we obtain the consistency equation. Reading sigma bar is equal to tanh hyperbolic of beta times h plus cj sigma bar, or for h equal to 0, sigma bar is equal to tanh hyperbolic cj beta sigma bar. As for the nematic phase transition that we discussed in an earlier clip, we see that depending on the prefactors cj beta, there is more than one solution to the consistency equation. For temperatures kBTC smaller than 2 times the dimension of the problem times j, there are 3 solutions, and we get a stable mechanization even at 0 external field. Beyond that temperature, there is no residual mechanization. The critical temperature in the case of a ferromagnetic material is called the Curie temperature. To summarize, the Ising model describes the phenomena of ferromagnetism. The internal orientation of magnetic moments that we derive by applying a magnetic field will survive even if we switch off the magnetic field. The residual mechanization will drop by temperature. If we apply temperatures higher than the critical temperature, the Curie temperature, the residual mechanization will drop to 0.